Hello, my name is Masoud Ataei, and I am pleased to present our paper, DAREK-Distance Error for Kolmogorov Networks, accepted at IEEE ICASSP 2025. This work is a collaboration with Professor Mohammad, Khojasteh, and Professor Vikas, Dhiman. Ensuring safety in autonomous decision-making systems is a critical challenge, particularly in high-stakes applications like autonomous driving, robotic navigation, and medical diagnostics. As these systems operate in increasingly complex environments, their ability to make safe decisions under uncertainty is crucial. Real-world systems are inherently uncertain due to sensor noise, environmental variations, and modeling errors. Because of this, deterministic models are often inadequate, and conventional deep learning models tend to be overconfident in their predictions. To address this, researchers have developed uncertainty estimation techniques to quantify model confidence. However, methods like Monte Carlo dropout and deep ensemble, which rely on probabilistic techniques, produce unbounded uncertainty bounds that require careful calibration and lack explicit distance awareness, meaning their uncertainty estimates do not always increase as data move further from the training data. Gaussian processes, GPs, the gold standard for uncertainty quantification, provide smooth and distance-aware uncertainty estimates, but suffer from poor scalability, making them impractical for large-scale applications. In contrast, worst-case analysis provides a different approach by focusing on computing error bounds rather than probability distributions. We introduced DAREK, a framework that provides distance-aware, interpretable, and computationally efficient error bounds for spline-based neural networks. Kolmogorov Arnold representation theorem, CAT, states that any continuous multivariate function can be represented as a superposition of single variable functions combined with addition. Splines are smooth, piecewise polynomial functions which can flexibly approximate complex functions while ensuring smoothness and continuity. Kolmogorov Arnold Networks (CANs) replace the univariate functions in CAT with learnable splines, effectively transforming CAT into a deep network rather than a simple two-layer model. CANs retain interpretability, efficiency, and robustness, making them an attractive alternative to traditional deep networks, especially for regression tasks. Building on this, DAREK introduces tighter and more reliable uncertainty bounds through a distance-aware error estimation mechanism. This mechanism integrates interpolation error and errors at nodes, with nodes selected from the training data. Using a modified CAN, DAREK balances the accuracy and efficiency of parametric models with the interpretability of non-parametric models. Consider a spline neural network like CAN. A layer of this network maps a d-dimensional input to an n-dimensional hidden space using a linear combination of splines. This process is repeated layer by layer to generate the final network output. In DAREK, we introduce a piecewise polynomial error analysis (PPE unit), which computes error bounds for each spline alongside its estimated value. These error bounds are propagated through the network, layer by layer, using the Lipschitz constant of each layer. Each layer's error contributes to the final output error. Errors from previous layers accumulate as they pass through network, and the final error bound at the output layer captures the total uncertainty. A layer of DAREK algorithm receives inputs from the previous layer and applies a PPE unit on them. PPE unit computes both the prediction and its associated error bound. The predicted output is obtained as a linear combination of spline-based estimations, ensuring a smooth and structured function approximation. The associated error is a combination of error introduced by current layer, which is computed directly within the PPE unit, and the propagated error from previous layers, which is scaled by the Lipschitz constant of the current layer, to account for its influence on the overall error bound. This process is repeated across all dimensions, ultimately providing a structured, interpretable, and distance-aware error bound for the next force output. For a more formal specification and proof, please check Theorem 2 in the paper. As previously explained, the PPE unit consists of three components: the prediction that estimates function value using a spline approximation, the interpolation error that calculates the error of a spline that passes through knots, and the error at knot component that recovers the error that arises when the spline do not perfectly pass through the training knots. The spline error is the sum of the interpolation error and the error at knot. Newton's polynomial fit a case-order polynomial through k plus 1 knots, with coefficient determined using divided differences. When dealing with more than k plus 1 knots, a practical approach is to apply a sliding window of k plus 1 consecutive points, fitting a case-order polynomial at each step. The plots illustrate piecewise Newton's polynomial for different spline orders, such as 0, 1, 2, and 3, applied to an arbitrary function. While Newton's polynomial ensures interpolation through all k plus 1 knots, its approximation at a test point may deviate from the true function. To account for the test point, we can fit a k plus 1th order polynomial explicitly, including the test point. This guarantees that the approximation passes through the test point. Interestingly, one component will be added to the previous approximation, but we don't have function value at test point. However, we can find an upper bound for the additional term, which captures the error of approximation of function with case-order polynomial, as stated in Theorem 1 of the paper. We refer to this bound as the interpolation error, which relies on the Lipschitz continuity of true function. This bound is tight when the true function's derivative is equal to the Lipschitz constant throughout the domain. The derived error bound assumes that the value at knots is 0. However, in practical scenarios, this assumption rarely holds due to noisy data, imperfect function fitting, or differences in learning algorithms. As a result, the error at knots may become non-zero, introducing discrepancies that must be addressed in our uncertainty estimation. If we had explicit knowledge of the error values at these knots, we could refine our error bound accordingly by fitting a Newton's polynomial to the error observed at the knots within a local neighborhood around the test point. This approach constructs an error correction function that estimates how the error propagates within the region of interest. This correction mechanism ensures robust interpolation even in the presence of noisy data or model perfection. The refined error bound is formally stated in lemma 1 of the paper, along with its proof. We also show that this error bound is tight. DAREK ensures the tightest possible error bound for a spline at any given test point, under the assumption of Lipschitz continuity. However, when applying this framework to complex networks of splines, certain assumptions must be made due to two key limitations. First, we do not have direct access to the Lipschitz constant of individual splines, but only an estimate of the overall Lipschitz constant for the entire system. Inspired by the SNGP paper, we divide the Lipschitz constant equally and assume all splines share the same Lipschitz constant. While this assumption may not always hold exactly, it provides a reasonable approximation that simplifies computation while maintaining a structured error estimation process. Second, when considering error at knots, we can only measure the total error at each knot rather than the specific error contribution of individual splines. To address this, we assume that all splines contribute equally to the total error. Using this assumption, we distribute the total error proportionally across all splines, via the Lipschitz propagation mechanism. By adopting these assumptions, DAREK remains practical and computationally feasible while maintaining the core properties of distance-aware error estimation. To evaluate the effectiveness of DAREK, we conducted multiple experiments. In the first experiment, we applied DAREK to a simple cosine function using a one-layer spline network. This setup allowed us to observe how the error bands behave. As expected, DAREK's error band tightly enclosed the true function across the entire defined space. The results also confirmed the distance-aware property of DAREK. Next, we compared DAREK with GPs and ensemble on the same cosine function. Although comparing worst-case error bounds with probabilistic uncertainty estimation isn't entirely fair, this visual comparison provided valuable insights. We plotted the 3 sigma uncertainty bounds for GPs and ensemble and observed that DAREK and GP exhibited similar behavior, both producing a structured distance-aware uncertainty estimates. In contrast, ensembles displayed erratic uncertainty values, like a clear pattern, highlighting the limitation of ensemble-based approaches. Additionally, this plot illustrates the computational complexity of DAREK and GP for datasets with more than 200 data points. The computation time of GP increases dramatically, while the computation time of DAREK increases quadratically. Finally, we applied DAREK to an object shape estimation task using laser scan data. We trained a two-layer CAN with units 2, 21, and 20 knots to learn the sign distance function of an object boundary. The results demonstrated that DAREK's error band effectively enclosed the true object shape, confirming its robustness in real-world applications. In conclusion, DAREK is a novel framework for distance-aware error estimation in spline-based networks. And unlike conventional uncertainty estimation methods, which rely on probabilistic approaches or computationally expensive models like GPs, DAREK provides structured, interpretable, and computationally efficient worst-case error bounds. We explored how DAREK integrates piecewise polynomial error estimation into spline-based neural networks, ensuring that error bounds remains tight and adaptive to distance from training data. While DAREK offers a significant step forward in structured error estimation, there are several avenues for future research. Refining the assumption on Lipschitz division and error distribution across layers to improve bound tightness. Extending DAREK to higher dimensional problems, making it applicable to more complex real-world scenarios. Integrating DAREK into real-time safe control systems, ensuring robust decision-making in dynamic environments. Ultimately, we hope this research paves the way for more reliable and trustworthy machine learning models, particularly in applications where safety and uncertainty quantification are paramount. Thank you for your time and attention.